Okay, so let's continue with what we were left because of the bug, right? We open this software, and now let's give a comparative listening to the three different audio tracks for the same composition. The first is the one generated by MuseScore. Wait, okay. And the second one is generated by Ableton Live. Okay, the third one is by a human performer. Okay, it's played by a human. So I feel the third one kind of have more dynamics and micro timing and expressions there. So as I mentioned, I want to try the neural network with this human performed audio and see how their model really works. Okay, the Google Magenta model really works. So let me cut part of this audio here, probably this one. Let me play this. Okay. So actually, I did this before. Yeah, this is clip. It's the same one. And this audio is of 18 seconds long. Okay. So let me upload this into the model, into this neural network model here. And let's see how it performs. Upload file. Oh no, this summer. Clip. Let's see. Okay, so it takes some time to transcribe. So when it works, let's see. Let's switch to some other tasks. For example, MIDI format. Okay, so let's get into some real stuff. So this notebook talks about the processing of MIDI files and how to process this MIDI file. The first step is to transform this MIDI to CSV. So CSV is a format that is a file that is human readable. Okay, so it's human readable format, and CSV can also be opened, using Excel. So it contains the letters, characters, and all the information that can be interpreted by human. So to do this, there is a package. Okay, we'll talk about later on. So let's run this code one by one. Okay. So first is MIDI as music format. By skipping this part. So the first package I use is Music21. Music21 is a Python-based toolkit for computer-aided musicology. So it works fine last summer, but recently, like yesterday, when I opened this, it doesn't open anymore. So it seems the developer stopped to supply this source. So I guess it's difficult for people to use this now. But because it still runs on my computer, so I'm continuing to use this library. The file I'm using is another file. It's a single line melody composed by Bach using the cello. Okay. It's solo cello, a solo cello composition. The name is CS1-1. Okay, pre. So converter parse, and we will parse this file into Python. And here we can show this parsed file, parsed MIDI file here, visualize this in our notebook. Okay. Yeah, it's pretty slow. Maybe probably because I'm using, okay, this already generated. So maybe let's do this first. So this is after I upload the file, the clip, and this is what the model generated. Okay, the neural network model. Let's listen to this. Okay, how do you feel about this one? Maybe let me play the original recording, the original clip here, and compare. Okay. Now let's play the transcribed version here. So it seems it makes several mistakes there. Yeah, several notes are misplaced and not very clear. It's a kind of slides through the recording. And yeah, comparative to the original recording, it doesn't sound that well. But let me save this MIDI. And probably open this. Let me see. New lab set. But actually, I have this transcription already here. Maybe save this file to desktop. Okay, let me import the transcript MIDI we just downloaded here. Okay, there is only one track, because the transcription doesn't distinguish between the left hand and or the right hand. So you can see this is the visualization in piano roll of the transcription. So to play this, we still need to drag in our instrument here. Okay. So let's play. There are some mistakes, but workable. One thing I want to point you to is that, so these are the piano rolls. Let me enlarge this one to make better sense. So you can see there are grades, right? The grades, the fixed intervals here, but actually the onside of those notes, transcription notes, are not really on the grid. They're not quantized to the grid, right? Here. So it kind of encodes the expressive timing of the performance here. It's not quantized. So later on, we will compare this piano roll to our original MIDI file. So you will find the onside or the onside of notes in the MIDI file are actually right on the grid. So they are quantized because the MIDI file is transcribed from the sheet music. So on sheet music, it's specified time signature, key signature, and everything is right, in time. So the timing is fixed. But here in this transcription, the timing is more free. And also the dynamic is more free. The dynamic is presented here as a velocity, right? So when the neural network model transcribe the audio performance to the MIDIs, it also encodes its dynamics. Okay, so how loud the note is, and there is a dynamic, means various levels of volume of those notes. So you can see here in this velocity, some notes are louder, some notes are quieter, and this is quite dynamical, right? Close this one. Okay, so maybe let me play this again, and I will switch to the original MIDI file. Pay attention to the velocity and the dynamic timing. Okay, so now let me open the site we just. This is the MIDI file. Okay, when I enlarge this, you can see all the notes are right on the grid. Okay. Yeah, every onside, every note is on grid. It's strictly defined by the sheet music, and this velocity, right? It's just a line. Basically everything is over the same velocity. So here is quieter, maybe this is F, and this is MF, the dynamic marks on the score. But basically it doesn't have this dynamic, right? The dynamic range of the velocity. So everything is just a line. So let me play this now. Yeah, it sounds better than the transcript one. It's not because okay, so actually the dynamics, the velocity, the dynamic range, the dynamics of volumes, and the micro timing actually should increase the expressivity or the learning experience of the symbolic the symbolic music performance or the file. But here, because there are several mistakes in that transcription, and in this file there are also some control messages. So we'll talk about control message when we talk about MIDI files. That's underplaying here in this file. So when we play this thing here, what we hear is not only about the pitch, the duration, and the dynamic. There is something called control message that's governing this whole piece, which makes it sounds better actually. But in generally speaking, the expressive timing means that when the time are not quantized and the velocity of more dynamics will generally makes the listening experience feeling better. Okay, so so this is something I want to showcase here. Okay. Now let me go to this one. Okay, let's continue with the notebook. So here, after parse this file, MIDI file into Python, and I can show it in the Jupyter notebook. So this is actually an image. I don't know if it's PNG or in which format it is. So this is an image. Let me try to see image as. Okay, this is PNG. Okay, this is PNG image. So it the score shows as an image in the Jupyter Notebook interface. Okay, and besides we can read the score from Jupyter Notebook, we can also open it as a MIDI format in a software, because my Python my Music21 package in the Python is directly linked to Muse score. So when I run this command, this file will automatically open in Muse score, because I set Muse score as my default software to open the MIDI file. Okay, so here you can see this is the MIDI file, and we can listen to this one. Okay. Let me play this. It only shows the first 8 measures, because I specified here, right? Only shows the measures 0 to 8. So it only shows the first 8 measures. Okay. So here is a remark on audio and symbolic music. So this clip of 8 measures is 24 seconds long. Okay. And the typical sampling rate of music signal is 44100 Hertz, namely so many points, data points in per second. Therefore, it requires over 1 million data points to represent this small piece. Okay, so what we just listened to, these 8 measures of audio, actually requires over 1 million data points, which means over 1 million numbers to represent this. However, if you represent this audio using MIDI files in the MIDI format, they're only less than 200 messages. So it significantly reduces the amount of data we need to take care of if we're dealing with symbolic music. If you deal with raw audio data, then there's a lot of, it's quite messy. I mean, audio is encompassing, it can represent everything, but in terms of information and in terms of errors, right? The more messages you get, the more data size, the more data you need to process, it will produce more errors. So There are also some other examples. So we'll play this later on. So the next part is on read MIDI as CSV. So MIDI is a computer compatible file format, which is not directly readable by human, right? If you open a MIDI file using maybe text editor or text reader, they will be just, random information, random messages. So in order to interpret MIDI into something human readable, and then we can post-process those information, we need a way to read MIDI as CSV file. So here we will use the package called py MIDI CSV. Okay, so this is a Python library that bidirectionally converts between the binary MIDI format and a human readable interpretation of the contained data in text format expressed as CSV. Yeah, this is here, and you can install it easily using pip install py MIDI CSV. And other package I use is Pandas. Pandas is a Python data analysis library, because we are going to encode those file information in Python, and Pandas, the data frame in Pandas will be a very useful tool for dealing with the informations in CSV as a table, as in the matrix form. Okay. And another is NumPy. NumPy is a numerical fundamental package for scientific computing, right? Numerical computations with Python. So these are just basic packages. Yeah, Pandas. Yeah, especially if you deal with data sets and data sets, and Pandas is something you cannot avoid. Yeah, everyone use Pandas. Yes, the popular. Let me open this. Yeah, just introduction. Okay, 10 minutes to Pandas. Here are some basic tutorial for how to use Pandas, how to process those files. In the table and view data. And you can even plot the data in Python or Jupyter Notebook. There are also libraries for plotting, etc., etc. Okay, data frame. So we'll use a lot of data frame here in this work. Okay. Boolean indexing, etc. Okay, so convert MIDI to CSV. So this operation is pretty easy. You only use pm.midi to CSV, and you input the MIDI file here. The file is the one we just gave here. The file is the MIDI file, okay, of this composition, and you input the file there, and the CSV string will give you CSV here. Okay. If I run this, yeah, so this is the MIDI information interpreted in CSV format that can be read by us, right? So you can see there's time signature, key signature, tempo. Although for now you still don't know what that means and what the numbers are representing, but at least you can read those messages, right? So this is the CSV file we can read, and here we are going to write the file into a text, txt. What is called js.txt. Yeah, so it's a faithful representation of the CSV string. So printing it into a text file. And here, in order to understand what those messages mean, we can refer to this file called MIDI to CSV. And if you scroll down here, there's MIDI CSV file format. Okay. So you can see the file structures, file meta events. And these are the messages. And these are channel events, note on, note off, yeah, about the nodes, etc. So there's an example that's, yeah, it looks like exactly like what we just saw. So this is a really important and helpful file if you want to read, yeah, know what the messages mean in those CSV files. So we'll get into those details one by one and give you examples to illustrate and understand those messages. So to do file processing, it requires a lot of patience. Yeah, you need to look into those mundane details to understand those things. So there are some select events we are going to use in the notebook. The first is the header. It contains format and track divisions and the time signature, right? What time signature it is, and case signature, and tempo, right? At what tempo the music is playing, yeah, which is represented in the score as BPM or the tempo. Yeah, the tempo is here. The tempo is 100 here in this score. And note on, note off. When the note is on, so the on side and off side of the note. And the control. Control is generally something that's okay, that's over the corpus. So what's including control is like modulation or volume. Volume means the volume in different tracks. Okay, when you have multi-tracks, every track has its own volume, and you can pan those volume and pan an expression, sustain pedal. If you are playing piano, right? There are sustain pedal and soft pedal on piano, but these pedal information are not encoded in the notes. So you need a separate information to represent those pedals. So we will give an example of a piano kind of, you know, a piano performance or piano MIDI file without this information, without those pedals and with the pedals. There will be a fundamental difference, yeah, if you lose this information. And there also like reverberation, chorus, etc. So this file gives you a complete reference for the control messages. Okay, so this is the control number. This is the values. For different control number, it means it gives you different, you know, messages here. Damper pedal. Yeah. Because MIDI is does not only represent piano. There is also violin, although also electronic music instruments. So there are also like pitch bend or slides, or you know, sound controller, or even the filters, etc. This is quite a complicated one, because here we are dealing with the. So here this composition is in shallow, right? Solo shallow composition, but we will give you an example in piano later on to discuss the control messages. Okay, the next program C specifies the instrument, which instrument you are using for this composition. And poly aftertouch, yeah, it's made for polyphonic synthesizers, polyphonic music. Often provide independent aftertouch for each note. And pitch bend. Okay. And in this message, I talk about how I actually encoded those CSV information, the CSV string into the data frame. Okay, because if you open this, yeah, this CSV file we just compiled, you can see there are different numbers of fields. For example, tempo only have only have 4 fields, but this message has 3 fields, this has 6 fields, and some have 7 fields, even longer. So there are different fields, which means, yeah, the columns, the number of columns are different. But if we want to process the data using data frame, we need to make it in the matrix form, which means the number of rows, the number of columns should be the same for each row, right? So I designed some tricks to, to concatenate some -1 here if it doesn't have this field, and process those information into the last column, etc. So I'm not going into the details here. It's just field processing. It's not really interesting. But if you want to know, these details, please read it by yourself. So I basically designed 7 columns here, because for each track, for each event, there will definitely be 3 fields: the track, time, and type. But after that, so for those informations, they are of various length. This is why I have to design 7 different columns and design a way to fit in each message into the rows of the same number of columns. Okay. And here is the way I process this. I wrote it to aligned.txt. Let me open this one. Okay, now you can tell in this one, yes, everything is of 7 columns. Yeah, 1, 2, 3, 4, 5, 7. Even for this one, 1, 2, 3, 4, 5, 7, 8. Okay, so this is 8. Oh, is it? No, 7. 1, 2, 3, 4, 5, 7. Yeah, it seems. Oh, it should. There's something wrong. Yeah, there should be something wrong here. But maybe this is the text. So wait. Oh, right. So this is just a way to write down those things using the commas to separate those fields. But I haven't write it into the data frame. So when I write this into the data frame here, you can see my data frame. The PD is pandas, has 7 columns: the track, time, type, channel note, velocity, and the value. These 7 columns. So there are some nuances going on when I design this file. Maybe I discarded some information here. Okay, those details are encoded in this block. Okay, if you want to, you can give it a closer look. And this is the data types of this data frame. Okay. So here, next one is understanding MIDI messages. So we can group. We can use the group by to group those informations by the type. Okay, so type is one of the columns. So this is the type. So we can group everything in this type. So you can see there are, yeah, these many types: Control C, note on, note off, etc. And this, and we can print the length. There are 6 different types of controls and the indexes. Okay. Okay, so these are the basic ways to extract something, to get some sub-data frame from the given the entire data frame. So now let's look into some events, like header. So header has the first 3 fixed fields, and the next, these 3 fields are format, number of tracks, and divisions. So these are the meaning of this. The MIDI file type is 0, 1, or 2 is the format. Number of tracks means how many number of tracks is in this file. And the more important information is division, what we will use in our numeric computations. So division gives you the number of clock pulses per quarter note. Okay. It means for every quarter note, how many numbers of clock pulses are there. So the number of clock pulses actually determines the time, the time here in the second field. So if I run this header, give the length, and PPQ is the pulse per quarter. Okay, we call it PPQ. It encodes the division. It encodes how many pulses. So in this file, we have 480 pulses per quarter note. So for every quarter note, the time will increase 480 numbers. Or yeah, this is just a time division in this MIDI file. Yeah, hope it's clear. Probably. Yeah, if you have any questions, just feel free to ask. Okay. If I'm going through this too quick or yeah, anything not clear. So the second information is tempo. Tempo gives the number of microseconds per quarter note. So this is a much finer division of the quarter note, which is in microseconds. Okay, so think about this. This number is super large here, right? So if we run this file, we can see the tempo. Yeah, there are different tempos. Different tempos correspond to different BPMs, beats per minute. So MSQ means the microseconds per quarter note. So the first MSQ is this 750,000 microseconds per quarter note. And to compute the BPM, we use right 60,000. Okay, so where this number comes from? Because this is MSQ is the microseconds, right? Microseconds, and the BPM is beats per minute. So how many microseconds are there in 1 minute? So we know there are 60 seconds, right? Let me do this annotation. 60 seconds for 1 minute and multiplies 1,000, we get milliseconds, right? And we need to multiply another 1,000 to get microseconds. So this is where this large number comes from. And when we use this large number to divide, MSQ is microseconds per quarter, and we get how many quarter notes are there in 1 minute, which is beats per minute, right? Beats. So 1 quarter note is 1 beat. So how many beats are there in 1 minute? Is 80. So this MSQ actually gives you a BPM of 80. Okay, is this clear? So this is the basic way of how do you derive the beats per minute information from the MIDI file. Okay. And with PPQ and MSQ, these are the time division units. We're able to discuss time in MIDI appropriately. So now let's talk about note. The note is the most fundamental components in the MIDI file. A lot of note informations. So there are a note on, and sometimes there are note off, sometimes not. So for example, in this file, there is only note on, but there's no note off. So the question is, if there's no note off information, how do we know the note is off, right? So how do we know when the note terminates? The method is that actually they use the velocity to indicate. So when the note is on, the velocity is of some number larger than 0, right? Which means there is a volume for this note and the note is on. And when the note is off, the time is the same, but the volume becomes 0, which means, yeah, when the velocity of the note comes to 0, the note naturally terminates. So instead of using note off message, they use this just one type note on, but they use different numbers of velocity to indicate the notes on and off. So here, I'm writing this out because there's no note off. So I'm manually designing another data frame that indicates the note off. So here you can see I extracted all the information of velocity larger than 0 as note on, and this information of velocity equal to 0 as note off. And these are data types, and the length of note on is equal to the length of note off, right? So once a note is on, it has to be turned off. It cannot last forever, right? So there's if we want to compute the duration of the note, there must be a note on message and the note off message. And going back to this function, actually, I changed this part, okay, comparing to my original file last summer, because the append, I used append in the previous file, but this function, doesn't work anymore in this new version of Python. Therefore, I replaced this with this concat function. So here, with the note on and note off information, we can compute duration. Okay. So note on, if note on is on time 0, note off is on time 120, the duration is offset minus onside, which gives you how long the note is on, is 120. So 120 is the pulses, right? In order to convert this number to quarters, we can divide this by PPQ, pulse per quarter. So we have 120 pulses, and our PPQ is, if you remember, we just derived this. Our PPQ is 480. Okay. Therefore, when we use this duration, 120 to divide this PPQ, we get. Okay, so 120 is the pulses, number of pulses, and this is the number of pulses per quarter. And if we compute this, we get the duration of quarter node, okay, of our node, which is 0.25, and this is 1/4. 1/4 of quarter node, which means it is a 16th node. It is clear. I hope this is clear. Okay. Let me see. So there are 480 pulses per quarter, and we have 120 pulses, which means these are just 1/4 of a quarter, right? So 1/4 of a quarter is the 16th node. If you do the math correctly. Yes, clear. Thanks. Okay, thanks for the feedback. Yeah. Yeah, I think the code is somehow, if you never read Python, a little bit, but they are basically just mathematics. Yeah, you don't need to write the code by yourself. You just need to understand the concept here, the math, like how you compute this, and then you can just do it by yourself, like manually. It doesn't matter. Yeah, the main goal of this code is to understand MIDI files, the MIDI format, because we talked about the symbolic music representation here, right? So this is the topic of our first lecture. So in order to introduce you what is MIDI format and how the MIDI format, how the MIDI messages are encoded in the file, and how to read it, how do we understand that, so that's why I'm introducing it. Oh.